Hello. Um, we considered the cost and output example to introduce the regression model, to motivate the regression model. And I am going to first show you how to obtain the estimators. So remember, we are going to estimate beta 0 and beta 1, and we will denote them as beta 0 hat, beta 1 hat. So when the data are given, Excel will calculate that for you, or a statistical software is going to calculate that for you. So let's have a look at the data. This is the data, exactly the same data set I showed as an example. So in January, I produced 2 units, then it costs $15, 3 units, 15, and so there are 12 observations, 12 by 2. So 12 pairs of observations. And we are going to use regression model to estimate, to predict the cost. How do we do that? We go to Data tab and Data Analysis tab here. Go to Data Analysis. Then you can find regression option. Regression, okay. Input y range. Y is the dependent variable. In our case, cost is the dependent variable, and x is output. On the right hand side, independent variable, and labels. The first row is label, and plots, residual line fit plots. Let me check it so that we can have a chart, a plot together with it. Then OK, I'm going to click OK, OK. Yeah. So this is what you get. So there are a lot of numbers. A lot of numbers we obtained. Let's see what they are. There are, first, let's look at the first 3 panels, 3 tables. This is just a, by the way, this is just a graph. The red among here, red is the predicted cost, and blue is what you observe. Blue is your observation, and red is the predicted cost. I may change the line, so you can draw a trend line like this. This is the visualization of our linear regression model. Exactly, this is what the same graph I have in the slide. And what the most important part of the table is this area. So this area shows coefficient estimate. So intercept is estimated to be, let's simplify this, estimated to be 8.189, about 8.2, and the coefficient of the output is estimated to be about 2.383. They are calculated by a method called ordinary least squares, which I'm going to explain later, but just for a while assume that they are given. So it looks like the fixed cost is 8.2 and estimated to be about 8.2, and the marginal cost is about 2.38, right? That is our result. And there is a familiar column, standard error. Now I guess you understand what they are. They are standard error of these estimators. Remember, standard error is the standard deviation of the estimator. So exactly the same definition applies here. And t statistics and p-value, I'm going to explain what they are for. They must be some kind of hypothesis testing, and I will tell you what they are later. And here, lower 95%, upper 95% are confidence interval. 95% confidence interval. So you may change the confidence level when you set the option, when you implement regression, and here the default is 95%. So 95% confidence interval is obtained. And okay, let's focus on these two parts. Your beta 0 hat, beta 1 hat, and their standard errors. Let's go back. So same result I captured. And we are going to think about, from this result, we are going to think about three aspects. First, we will approach beta 0 and beta 1 using the estimation and hypothesis testing theory. So we can apply the theory like confidence interval, p-value, and other things to those parameters. So we will study how it behaves as an estimator. And second, we will think about the prediction. How can we predict? Which is actually easy. This is easy, but this is the purpose of, the most common purpose of doing this work, using this model. And finally, we will study the behavior of the error term. The error term means something, so we will, especially it shows how accurate your estimation is and how correct your model is. So we are going to look at the error terms in the third part of the slide, the chapter. I'm not sure, maybe we may be able to do up to this point, or maybe here. Let's see. So think about the slope, beta 1. In our case, as you see, this is beta 1. This is beta 1. 2.38 is beta 1, and its standard error is 0.206. So this is beta 1. And first, we can apply it. It is nice. It is a very nice estimator. So it has many desirable properties. First, they are unbiased. So beta 0 hat and beta 1 hat are unbiased in the sense that their expected values equal to their true value, right? And we know their standard error. Standard errors are given, and also theoretically it is proven that those standard errors are the minimum possible standard errors among some comparable regular estimators. It's this what does regular estimator means? That's more of mathematical assumptions. So I would, if you're really curious, send me an email. I can send you a mathematical result. Anyhow, it's nice. Everything is very good, and everything is very nice. Your estimators work really well under mild assumptions. So they are nice, as we the results are nice results. So we just understood what they mean. And standard error of the regression is calculated a little bit different way from other estimators we learned before. So the standard deviation of epsilon determines the size of error in the model of estimation. That means, let's go back to the equation. In this equation, the noise epsilon is a random variable, so it has its own standard deviation. And if its standard deviation is large, that means there are more noise. And if there are more noise, then it will be more difficult to correctly identify beta 1 or beta 0. So the more noise in epsilon, the less accurate beta 1 will be. So the large its standard error will be, right? And then put it this way, the large epsilon standard deviation is, the more noisy your data are, so the less accurate beta 1's estimator is, so the greater the standard error of beta 1 hat, right? That's That's the thing. And so the point, the standard error of the regression, is usually denoted by S epsilon, and it is calculated as the standard deviation of epsilon, right? Standard deviation of epsilon. But another strange thing happened here is n minus 2. Denominator has n minus 2. The idea is, why do we have n minus 2? Because, let's think about this. In variance, when we calculate the variance, we used n minus 1. And the simplest possible intuition behind it is that when you have one observation, you cannot calculate the variance. But if you have two observations, then you can define the variance. All right. So the variance can be calculated with at minimum of 2 observations. In this case, in this regression model, epsilon, so when you have 2 observations, then you can draw a line. But there is no error. In that case, you can draw a perfect line, but there is no deviation up and down from the trend, right? Whenever you have 2 points, you can draw a straight line going through 2 points. So the standard error is not defined. Standard error of epsilon is not defined. But when you have 3 points, then you can calculate something for this guy. So this guy can be calculated with the minimum of 3 observations. That is why. So intuitively, that's one way to understand this. And a more statistical way is that the minus 2 is because we already consumed 2 information in estimating beta and beta 0, beta 1 and beta 0. So that's another intuition. So you have to consume your amount of information in estimating those 2 parameters. So you have to subtract 2. Anyhow, if it's not familiar, then never mind. And it is, where it is standard error. This is what I just explained. So 1.6 or 1.716 is the standard error of epsilon, the distance between your observation and the trend line, right? That is how we calculate this guy. So it's here, I just explained. And standard error of the slope. So previously we just calculate the standard deviation of epsilon, but now we are calculating standard deviation of beta 1 hat. It is an estimator. So this is calculated this way. First, numerator has epsilon, standard deviation of epsilon, which is the amount of noise in the data, right? Epsilon is the noise, so it captures how much noise you have. And in the denominator, you have n minus 1. So as n increases, the standard error decreases. But what is strange here is standard deviation of x is here, right? You may think this is because beta 1 is multiplied to x. So as a mathematical byproduct, at some step, like originally beta 1 times x should be rearranged by dividing it by x. So on both sides, x is divided. So it happened to come here, but at this time, it's not that important. The point here is the noise and the sample size. The amount of noise and the sample size are important components, which is comparable to the standard error of the sample mean, right? Sample size and the noise in the data. Okay, so that is given in this column. So standard error is calculated for each estimator. So 1.17 is the standard error of the intercept estimator, and 0.206 is the standard error of the slope. Okay, so like this, we are going to study the results one by one. We will figure out what they imply one by one. So I'm going to continue that in the next video. Thank you for watching this.